turn to 30 right when. Okay. I meant to do that. All right, folks. Let's get started. Okay, so we are talking now about cryptography. We started off a little bit on this topic on Thursday. Someone remind me what types of security properties can cryptography maybe help us with? Of our three main security properties that we care about. Yeah.
Confidentiality.
Confidentiality, what else?
Integrity.
Integrity. And what are some other maybe lesser security properties that don't fit into our CIA triad? Yeah.
What's authenticity?
Close. Authentication?
Yes.
Most of the same words?
Non-repudiation.
Letters. Non-repudiation? Yeah. So these are other properties that cryptography can allow us to accomplish. So what is the Caesar cipher? Somebody remind us an overview of what the Caesar cipher is. Yeah.
Take each letter and add 4 to it. So like.
Take each letter and add 4. How do you add 4 to a letter? Those are numbers and letters. They're two different things.
Well,
type error.
ASCII values.
Yeah. So two different ways, right? You can think about it in terms of just shifting, right? So you have all the letters A through Z. If you're adding 4, you're moving it 4 down the line with wraparound. Or you can think of converting each letter to its ASCII representation, add 4, and mod, and make sure that goes all the way around. No, I wasn't picking on you in particular. I just didn't make that point before. Cool. Okay, so then we can think about, so we have this basic notion of the Caesar cipher. So if we are adding 4 for encryption, then what's our decryption operation? Subtract, yeah, go back 4. Great. So the idea being, as long as we know the key, we won't be able to decrypt that message. So we can think about a Caesar cipher in terms of a crypto system that we've been talking about. We can say, well, the M is, and this is important, we can't have arbitrary letters, right? We can only, we can only have letters. So we're only thinking A through Z. So what other characters do we not have? What was it? Punctuation marks. What else? Yeah.
Kind of spaces too.
Spaces. I'm not a grammar person. I don't know if those are the same thing or different, but I'll take it. What else? Special characters. You want to say emojis or just in general special characters?
Exclamation mark.
Okay. Exclamation mark. Yeah.
Could it be like accents?
Yeah. Accents. Numbers. You can't even use numbers in this system. You're only limited to A through Z. So is that a major flaw in our crypto system? Will we be able to communicate if we only have letters?
You can spell them out.
We can spell out numbers if we need it. What else? What was that? That is funny. Okay, yeah, so you can encode it in Roman numerals. I think that would work. What about spaces? Do you often send text messages to people with no spaces? Is it impossible to communicate with that? Yeah, it's not impossible, but it's just annoying. So we can assume that the other side will be smart enough to decode properly and to put spaces where spaces need to go. So for this system, we're going to say we're ignoring that. Then we need a key. So in our case, the key is going to be an integer from 0 to 25. Why this range? How many shifts are in that range?
26.
26, excellent. And so why 26? Yeah, 26 letters. So every possible shift, right? So think about there's 26 possible shifts, 0 being no shift, right? Okay. And then we can define our encryption operations just like we said them. So if we assign each letter a numerical value, 0 through 26, or 0 through 25, we can encrypt with the letter of the letter's numeric value plus k, so shifting it over, mod 26, and then we can subtract mod 26, and our ciphertext is the same as the message. So we're not going to magically encipher something and get spaces out of it. Right? Spaces are essentially meaningless also in our ciphertext. Okay. How do we attack this? Do we want to go over an example? Do you want to encrypt something? All right, what's our K? Somebody make an easy K.
3.
Good. 0 is too easy. All right. Our message, let's say hello. Let's go more. World. Right? So no space. All right. So what's our encrypted ciphertext then? Okay. I'm just going to take the first thing that somebody says, so you should all be double checking each other. What was it? It can't be L. I know one. Okay, good. So O, and we know the next one must be O too, or as well. And then what about O? I just heard like 3 different things. Oh, not triangle?
Not triangle.
You should be more specific. Okay. R. Okay. W. Z. O. We know is R. R is U. L. We know is O. D. G. It's V for R.
Shouldn't the second letter be H as well?
Wow.
Counting up.
So maybe this is a very secure crypto system. I would say this was V.
STU. There should be U.
U.
No, because
I just can't keep wrong this. We'll go with this for now, whatever. It actually matters. Okay. Okay, so.
No, that's right. That's right.
So now, and we could decrypt this, so if I just gave you this message, you also need to know the key in order to go backwards, right? Okay, so then what are some attacks that we can perform on this? So let's think about it in 2 different ways. So what are different types of situations? So put yourself, let's, I don't know, we'll first put ourselves back in Caesar's time. So we're sending a message, hello world, to one of our generals for some reason. And we're sending this message along on a courier. What are some things that an attacker could do? Yeah.
You can use brute force to like check against every key.
Oh, but how do I brute force it? I don't even have the message at this point. Yeah.
Well, I'm assuming that one of the first things you would try is a direct mapping function. This is, so you might start by looking at like recurring letters, and then maybe recurring patterns of letters. So you might reason like, oh, these 3 letters keep recurring. Maybe they're a common word like the.
Yes. Let's hold on to that for 1 second. How do we even get to that point in the first place, right? So let's say I'm Caesar here. I have my general over here. I'm sending. Well, this is gonna be. I'm gonna call myself C-Hack because I don't know. So I'm sending out a messenger, right? So messenger with the message M, and that's what's getting. I'm just gonna call it M. So messenger, right? So you're an attacker. What do you actually need to observe to start attacking this? Yeah.
I have to find your messenger.
You need to find the messenger, right? If you don't have the message, how can you possibly infer what the message was? Although I guess technically, depending on what this general does, maybe you can infer what the message was, but that's going a little bit too far for what we're talking about here. So at some point, so I'm some barbarian. There we go, this works. I'm the barbarian Adam. That works. So intercept this message. I get this message M, or C. So I'm getting this ciphertext. So now we can talk about, okay, how do I try to break this, right? So the important thing to look at is to think, looking at just this one message, right, of the letters that were in the plain text and in the ciphertext, what are some similarities and some common patterns that are still present when we encrypt this plain text message? What was that? Yeah, so not just that they're next to each other, but they're also repeated, right? So just what we were discussing earlier. So we have patterns. So we know that because every element, every message, every character in our plain text is going to be mapped to the exact same character in the ciphertext, we know that there are at least 3 of the same letters in this plain text. Right? And we know that 2 of them are next to each other. Right? Because we know that all of the L's map to O's, so we know that there are some patterns that are still in the encrypted text. So how can we use that knowledge of patterns maybe to help us try to decrypt this? Yeah.
Think about words with 2 letters next to each other.
Yeah, you can think about what are all the words that have 2 letters next to each other, right? You could look through the dictionary, you could figure this out. You're a computer scientist, you could write a program that just does this and spits out all the words, right? And then you could try to see if what shift would properly fit where that is and test to see if the rest of the message actually makes sense. Yeah. Cool. What else could you do? Yeah.
Brute force and create the 26 different sequences by doing increments of 1, okay?
Yeah, so I could maybe try, well, I don't need to try 0 because otherwise I would be reading this message. So I could try all the keys from 1 to 25 and see, just try all of them, write them all out, and see, does any of these actually give me the correct answer? Right? How would I know it's the correct answer?
Does it make sense?
Yeah, because it makes sense, right? Because there's semantic meaning in the message of whatever it's supposed to be in whatever language that is. What if I can't read this language? Yeah, I mean, I'm already kind of not going to discover the meaning, right? You have to, in some sense, assume you already know what the language is. But if we try this, we could try, I don't want to write all this out, but you could try every variation of this, and one of these variations will be hello world. Right? And we don't necessarily have to worry about all this other stuff. Okay, cool. So we talk about that. This is also, did I already mention this, for coding interviews? Lots of heads looked up. Oftentimes when they're asking you to solve a question, so 2 things. A, they usually underspecify the problem. So they just say, I don't know, solve this problem, and part of it is they want to see your ability to figure out the specification of the problem. So you could say things like, I don't know, is it possible for this parameter to be null, or all these kinds of stuff. So they want you to actually, what they don't want is for you to just like think for 2 minutes and just write down the correct answer. Right? They want to see somebody who can work with them to understand what's going on. The second thing is, the best way to stall on that is to say, well, let's do the brute force way first, because whatever, if it's sorting sorting some lines of text, sure, you can implement a quick sort, but if your lines of text are only ever going to be 10 lines, then who cares what sorting algorithm you use? So as long as you can start maybe going down that path, it's usually always nice to think about brute forcing the problem first and then moving on to more complicated things. And it gives you time to think about what way you want to go forward. But anyways, and this works here. And why does this work well here? What was that?
It's short.
Short, yeah. The number of things we need to brute force is very short, right? We only need to brute force 25 things. This is something that you could all do right now. I guess I won't make you do it, but you could. Okay. So we can brute force. We could also look at, this was a technique we talked about a little bit maybe. So we can look at 2 grams. So 2 grams are characters that appear next to each other, so that's the 2. So 1 grams would be the frequency of 1 character appearances. We can look at what's already mentioned, the 2 character appearances, because we know that there's 2 of the same letter that follow each other, and so we could try to look for what words, and maybe rather than do a brute force, do more targeted brute force. Okay. Cool. Okay. So what if, so in this scenario, I was able to steal the message, right? What if, okay. So I'm going to make a big box called E. It's going to stand for encryption. So I have a message coming in on one side and ciphertext coming out. So what if I can't break into this box? It's a very well secured hut, back to our Caesar days. But as an attacker, I'm able to steal both the message and the ciphertext. So I have the message and I have the ciphertext. How can I break the key? Yeah.
If you know the method like this one, you can just check what the offset is between the two.
Yeah, this would be very easy, right? If I don't know the key and I just have this is the message, this is the ciphertext, I can take the delta between each of the characters. It's going to be 3 in this case. And there we go, that's my key. So then I can decrypt all possible messages after that that are encrypted with that key. And why was that easier than just having the ciphertext? Yeah.
Because you had something to reference to as what is the single source of truth.
Yeah, so I had more information, right? I don't just have the ciphertext, I have the ciphertext plus the message. And what if okay, what if I again have an encryption hut and instead of stealing a message that's going to be sent to be encrypted, what if I dress up like one of Caesar's scribes or something and I put my own message in? So I put like message prime and they give me back ciphertext prime. What should my message be so I can quickly and easily discover the key?
The alphabet.
The alphabet, but that's long. What else? What do I really need? A, just one A, right? If my message is one A, what's my ciphertext going to be? D, which I know is 3 from A, so boom, done, right? So this is 3 different ways that we can think about attacks on a crypto system. And each of these, an adversary has a different level of capabilities. So we can go and think about, so this case would be you're sending some encrypted message over the internet and somebody's able to intercept that transmission, read it, and maybe they can try decrypting it. So this is a, let's see. Yeah, so this would be ciphertext only. So this is, the attacker has access to the ciphertext and that's it. And they may have access to multiple ciphertexts, so we can talk about that later, but they have at least one ciphertext. Whereas here, they have a known plaintext. So they know the plaintext and they know the ciphertext. And how's that different from our third option?
We have a very simple plaintext.
Well, maybe that's not necessarily simple, but we chose the plaintext, right, as the attackers. Yes, and we made it simple to take advantage of weaknesses that we know in this crypto system. We know if we give it an A, it'll essentially tell us the key right back, right? And we got to choose the message in this case. So these are the 3 kind of adversary capabilities that we think about. Okay. Ciphertext only, known plaintext, and chosen plaintext. And these are essentially in order of increasing capabilities of the attacker. So it's important, and we'll get to as we get to more and more. If you, let's say, design your crypto system such that it's only secure against a ciphertext only attacker, that maybe is not good enough, right? So if you think about what's oftentimes like a chosen plaintext, like a web server, you're talking HTTPS, so you're talking a secured communication to a web server. It may include some of your content in the web page that it sends back to you, that it's encrypted with its server key. So you're choosing the plain text that it's encrypting, and so if you can take advantage of that, you can attack it using this model, but you want your things to be resistant to that. The other point we need to get to is what assumptions should we make about the adversary? So should we assume that the adversary knows the algorithm used? Yes, no?
Because you don't understand their capabilities fully, so it'd be best to assume.
Yeah, so if we're trying to make guarantees about the security of a system, we should maybe assume the strongest possible adversary. And that would be somebody that knows exactly how the system works. Should we assume they know the key? That'd be a pretty strong adversary.
Like, there wouldn't be no way to defeat that.
What?
There wouldn't be like a way to defeat that if they had the key.
Yeah, based on our crypto system, right? If they have the key and the ciphertext, they can decrypt the message, right? And they can even encrypt messages that we can decrypt. So, yeah, so the fundamental assumption is we're assuming the key is secret. It's something that must be kept secret. But the adversary otherwise knows everything about our algorithms. Is this a realistic scenario in practice? Seems pretty reasonable to think like, well, I can just make some crazy crypto system and nobody's going to be able to understand how it works, therefore it's secure.
It seems reasonable because if they have a way to get your encrypted messages, they probably could figure out roughly what method you're using to encrypt them.
Yeah, so if they have access to maybe the software that's doing the encryption, right? They don't have your key, but you need to talk to people. So, I guess the other way to think about it is once you become enough value that somebody cares about breaking your system, they will do whatever it takes to figure out how it works, right? So yeah, for multiple reasons, right? From a security perspective, we don't want to rely on just the other way to think about it is now how your system works becomes essentially the same as your key, right? So you need to protect that with as much secrecy as you would protect your key, which is way more difficult than like one integer. Now you have to keep how your whole system works, which is very difficult. Cool. Okay, awesome. So we actually already started talking about attacks, right? So we can talk about mathematical attacks. We can identify vulnerabilities in the underlying mathematics of the crypto system. We'll see some examples of these when we look at other things like RSA and DES that have been known and shown to be vulnerable, and that an attacker could break them faster than brute forcing. The attack that we'll look at a lot in this section is more statistical attacks. Right? So when we say statistics here, what do we mean? Yeah.
Like letter frequency, maybe?
Yeah, like letter frequency. So why is that important? So is every letter in English equally likely? No?
No.
Why not?
Vowels.
I don't know, stuff, because that's how it is. Like, I don't know, you can look at all the letters in the English alphabet, you can look at the frequency of letters used, you can analyze text that's been used, you can come up with a very good model of the relative frequency of each character. Yeah.
You can target words. I mean, if you're talking about like Caesar, I mean, the word like attack and like legion or something like that might appear more frequently.
Yeah, so then we can even think about targeting our statistics for the specific domain that we're interested in, right? Essentially our adversary's language, but we should be able to come up with probabilities and statistics of those languages. Cool. So yeah, we can basically, and the essential idea is examine the ciphertext and try to smartly figure out what things to decrypt and maybe what keys to try based on knowledge that we're understanding from the ciphertext. So you can think of that it should be the case that no statistical properties relate from encryption. And we can see this already in the Caesar cipher, right? You all looked at that already. All the L's get mapped to the same thing, so you can see that there's two letters that are next to each other, right? And all L's get mapped to the same letter. But even if all this stuff is 100% secure, and again, this is why I'm trying to harp on the do not write your own crypto system, even if you get this 100% provably, formally correct, mathematics, all great, the statistical assumptions, you've proven that they're not possible to do those attacks, you can still have attacks against the implementation itself. And so these are vulnerabilities where it's the implementation itself. So maybe it could be something silly like a buffer overflow that leaks the key, or that allows an attacker to control your system to steal the key. It could be like the, has anybody heard of the Heartbleed vulnerability that occurred a few years ago? So this was essentially in the, I think TLS or SSL, I can't remember exactly which one, but in the underlying secure communication protocol that HTTPS uses, there is a feature called a heartbeat. So say like, hey, are you alive? If you are, like, send me back some data. And so they would send you back data. But it turns out an attacker could trick the other machine to send back more data and read its own memory. And so by doing this enough, you could steal the server's private key and be able to decrypt network communications. So this was something that, like, the system itself was 100% secure theoretically, but due to implementation and coding bugs, you can introduce these kinds of implementation vulnerabilities. Okay, cool. So we're going to focus first on kind of what we call classical cryptography, and this will be more clear when we talk about kind of more modern systems. But essentially the idea is, and as we've talked about with Caesar cipher, the sender and receiver both have a key. They're either the same key or they're trivially derivable from one or the other. It's also called symmetric cryptography. So the keys are symmetric. They are essentially the same. So so then how does this actually work? So how do you then do this? How do you share a key? So going back to our Caesar cipher example, how did Caesar and the general know to use that key? Do you send them a message and say, also, by the way, the key is 4? Yeah.
They agreed on a key before the general set off to go to wherever they had to go.
Yeah, so you have to pre-agree on a key beforehand. And what does this presuppose about your adversary?
That they're not listening when you give the original key?
Yeah, that they're not listening when you give their original key, right? So think about even now. If you had to share a key secretly with somebody so that nobody else knew it, how would you do it? Any thoughts? In person, whispering. What about your cell phones on you? You know you're carrying a recording device with you at all times. If somebody hacks into it, can turn it on and record what you're saying. You have to make sure there's no electronic devices in there. You have to make sure there's no bugs or electronic listening devices in whatever room you're using. What else? Yeah.
Write it on a piece of paper.
Write it on a piece of paper, and then what?
Burn it. Show it to them.
And then hold it up to them, and then what? Yeah, you'd have to burn it though to make sure that there's no. You'd also have to make sure, what if there's a camera in the room that you're in? Yeah.
Engrave it into like the bottom of it, like a table. I guess it does basically the same thing, but like conceal it under something or in something.
Sure, maybe. Yeah, but where are you writing it down to then seal it into? Because you have to make sure that is secure, and you're not. Nobody can see what you're writing down then. Yeah. Ooh, but how did that system become secure? Where did the keys there get exchanged? Yeah, so that's a nice thing. If we had that, right, if we had a secure way to communicate, we can maybe communicate new keys or do something like that. We'll see that actually gets used later. But yeah, so this is the key is it's very difficult. So this is the the main problem. But if we can do that, then we get all kinds of nice security properties, and it's still used in a lot of places, so we'll see why eventually. But we're going to look at two types of ciphers that are exactly what their names sound like. So substitution ciphers, you're substituting one character for another, just like the Caesar cipher that we talked about. The other ones are transposition ciphers, where you're moving characters in the input around. And believe it or not, this is what the crazy thing is. I really like talking about these because we're going to study these older types of crypto systems that you could do by hand. And then we'll see that actually modern DES, AES is just made up of lots of these types of operations. And it's used all the time. Cool. Questions so far? All right. Okay. Substitution ciphers, and the classic example is the Caesar cipher. Oh, here's where we can check our work. Look at that. Hello world. Let's see if you did. You guys chose the same key that I did. Did you do that on purpose?
Sure.
I feel like I'm a mentalist right now. I tricked you into using the same thing. Core Zerg. Is that where we ended up?
Yeah.
Okay, cool. Sweet. So, Caesar cipher is one of those classic first examples of a substitution cipher. We're going to change every letter of the input into something else. So then we talked how to attack this, right? We can brute force, try every possible key. And in this case, it's very easy, right, with a Caesar cipher. There's 26 possibilities. We don't need any more than that. But we can also try to do interesting analysis, and this is the one thing we'll look at. We can compare the ciphertext with a 1 gram model of English. So what does that mean?
The occurrence of one.
The occurrence of one letter. Yes, letter. In this case, letter. Right. So the gram we're talking about is a letter. So 1 gram model of English is the frequency of each letter in average English text. 2 gram model would be the frequency of 2 characters appearing one after the other. And you can even go on 3, 4, all this kind of stuff. You can think about words. So how does that help us then attack the Caesar cipher? So let's say we have some ciphertext. It's not a ton of letters. I think it's roughly 20 letters. Right? So it kind of seems, one of the interesting examples is kind of looking at this and seeing that we could, that even the statistical properties we're interested in are still manifest themselves here. Even with like roughly 20, 25 characters, yeah.
Like looking at it, I noticed there's a lot of B's, and I know that E is the most common letter in English, so I can try that one first.
There's a lot of, say it again?
B's.
B's. Yeah, there's a lot of B's. There's also the thing that, so we also maybe at a higher level need to think, is this a, if we didn't know, we could say, is this a Caesar cipher or a substitution cipher or a transposition cipher where they're swapping positions, right? So we'd say, well, looking at this, there are, at least 2 Q's in this ciphertext, which is highly unlikely to happen just by moving letters around, especially because I don't see any, there's only 1 U in here too, so that's even more unlikely. Yeah, so maybe we look at common characters, right? Mostly all the V's are followed by H's?
No, the B's.
Oh, B. Oh, interesting. Okay, BH. Yeah, that's cool. So the 2 gram frequency, so starting at the beginning. There we go. BH, BH, BHE. Interesting. Okay, cool. So we can also think about it holistically, right? We can think, and you can easily go look up this information. This information exists. We can look up to go with our intuition of what actually are the most frequent characters in English. We can graph A through Z the average frequency of each character. So what are some of the kind of peaks that we see? We have E, A, T, surprisingly more than the other vowels, it looks like. So we have several interesting things here, right? We have, so A, but we have to kind of check ourselves. Are we going to expect to see the exact same distribution?
No.
Why not?
Too small of a sample.
Yeah, that's the other important thing to think about, right? This is the averages computed across a ton of English text. If you were going to compute this yourself, how would you do this?
Textbook or like
Yeah. Say again.
oh, grab a PDF or textbook and try to like calculate from there.
Yeah, so grab either one textbook, maybe a bunch of textbooks. There's Project Gutenberg, which has free text files of a lot of English books. You may be biased more towards older works, so that would be an interesting thing to keep in mind. But yeah, it's literally counting. You all can count. You can write programs that count. Yes. Right? You can count up how many times is that character appeared divided by the total number of characters. So you get all that information. And so you could make this graph, right? You could make this for whatever language you want. It could be German, which is going to be different, right? All the different languages would be different. But you can calculate this. So if we think about this graphically, what does, and this is what we're going to think about for different types of ciphers, what does applying a Caesar cipher to some text do to this graph? So if we think about this graph, let's say with a key of 3, right, like our example, what's it going to do to this graph? Yeah, let's go over here. Yeah, shift. So is it gonna, the key thing to think about is it gonna change any of the relative frequencies? No, but the other thing to think about is if we think about our message, right, our plain text message has its own set of frequencies, which are probably gonna be closely aligned with this, but maybe not precisely. And then it's just gonna shift those by 3. So by shifting it by 3, what does that preserve from this graph? Yeah, well, so in what sense?
It preserves kind of the shape of the graph to just shift it over.
Yeah, so shape of the graph, right? Meaning the peaks, so the characters that are most frequent will still be most frequent, just shifted over 3. The delta between characters, right? So if we look here, there's, which is kind of expected, there's not a lot of J's, Q's, X's, or Z's, and those are kind of fixed differences. So we'd expect maybe, and V is not very frequent, so we'd expect there to kind of be this, what is this, 1, 2, 3, 4, 5, like a 5-character stretch of low frequency in our cipher text. And that'll just get shifted, right? Cool. So then we can calculate that in our cipher text. So just like we discussed, we have, let's see, is B the most frequent? I think yes. So B is very frequent. So now if we wanted to maybe okay, yeah, now I see. So this is sorted by frequency, upper left to the right. So it's B, H, L, E, Y, R, Q, A, B, so on and so forth. Right, the most least frequent. So maybe if we were just going by this, maybe what would we try? What would we guess that B maps to? E? Yeah, so we can think of this as a maybe -4 shift, or whatever that is the other way. What's that, 21? So 21 around would get you there. So we can maybe try that, see if that decrypts. We maybe think maybe it's the next most, maybe T, and we'd maybe try that to see if that shifts, right? So we could just try matching up the most frequently used with the rest. Cool. We can, yeah, okay. So we can, so these are all different kinds of techniques we could try. So we could do this, we could do that by hand. The other thing we could do is we could try to take statistical measures to see how frequent, how does the frequency that we compute match up with this graph, essentially. So what we can compute is a statistical analysis, and we can say for every possible key, so we can try all possible keys and see essentially which one shifts the graph such that it aligns closest with the graph that we care about. So we can use, so P of X is the frequency of the character in English. That's the graph that we just looked at. We have all those frequencies. F of C is the frequency of that character in the ciphertext. And we can calculate for all the characters, what does that shift do to that character in this calculation. So this would be, again, it's kind of, here we still have to try all the keys, so kind of, this is a, I don't know, slightly more elegant solution than brute forcing, but essentially we're brute forcing all the keys, trying to calculate a statistical measure that tells us how close we are to being correct. So we could do something like this, you could do this, and you could say that, so we give you a sorted list of all of the keys. And then from here we could try those different values. So does that map kind of to what we thought? So 23 is maps D where? Is that or let's map it to T. You know what? We can cheat. So by 23 we get something that looks like this. Does that look correct?
No.
If we were writing an automated program, maybe, what could we do to try to score this to see if this is more correct? Yeah.
Check for common words.
Yeah, check for common words. We can get a list of common words and we can check and see, or all words, right? We can say how many words actually appear in this. Yeah.
You use like n-grams to see if there's any.
Yeah, we can maybe use more statistical measures, use n-grams to see if those are correct. We can see that this is not correct. We can see 13. Where does 13 put us? So we had B map 13, so 1, 2, 3. 13. B map to O. And then we see something that says you should never build your own crypto. Does that look correct?
Yes.
Yeah, so again, why wasn't this the first answer in our statistical measure? Yeah.
The sample size of letters wasn't big enough.
Right, we didn't have exactly, so the distribution we're sampling from for this message, A, there's not a lot of characters, and B, so there's not a lot of words, and B, there's, weird words in there like crypto and U and stuff, so it's over-representing things like Y, which we probably wouldn't expect to be in the message necessarily if it was random English letters. But it still cut down our analysis time basically from trying all 26 letters to and brute forcing those to just trying 3, let's say. Questions? So then what is the problem with the Caesar ciphers? We just broke it trivially. You could do this with literally pen and paper. You could just write out all 26 probabilities. Even if it's long ciphertext, maybe you only do the first 4 letters and just try shifting each of those by 26, 0 to 26. Hopefully you get something that makes sense, and then there you go. You don't have to actually by hand decrypt everything. Yeah.
Wait, how did that function you're using get you those values like 23 and 13?
So these are the I's. So we're calculating this metric for each I, which means each shift. So we're doing from 0 to 25. Then we're going to calculate and sum up from all the characters 0 to 25. Basically, the frequency of that character in the ciphertext times the frequency of the shifted character in the other text. I believe it's calculating the mean squared error or an error metric of how close your distribution matches that distribution. It's a lot of adding. So problems? Yeah.
Like you said earlier, it's really easy to brute force.
Yeah, it's really easy to brute force. So how would you make that more difficult? Yeah. Okay, maybe multiple keys. How else? Think about it in terms of our crypto system. Yeah.
You could use words in your set messages that you're sending to your generals or whoever you're sending it to that don't mean the same thing that
tricky.
typically means. So
Okay, so like a code underneath the code?
Yeah.
That's interesting. Yeah.
You could have a bigger alphabet.
Yeah, maybe a bigger alphabet. So you could use A through Z capital, A through Z lowercase. You could add punctuation marks. What would be some downsides of that or benefits? So the benefit would be more keys. So let's say we extended it up to how many numbers can a byte represent?
256.
256. So let's say using a byte per character, so it can represent 0 to 256. Right? So now our keys, instead of being 25, are 256 possibilities. Was that better? Yeah.
No, because then like
You came up with this. You're not fighting for it?
like this wasn't like the exact scheme. I was thinking like use a language with a bigger alphabet.
Oh, interesting.
If you have like just a normal 256 thing.
So you're blaming it on me because I wrote your keys. Okay, so what's the problem with it then?
The problem is that if you're switching over to like characters that are never used, then you know that you can kind of like it doesn't really help you any.
Yeah, so if you think about the graph, right? Our graph of English frequency. Imagine you had this, but then you had for uppercase letters versus lowercase letters versus the numbers 0 through 9, and then added on punctuation. Right? So you'll have vast swaths of areas that are never used. So it'd be pretty clear if you shifted into there roughly how much you need to go to get to something that actually makes sense. Yeah.
You could like insert you could insert noise that like makes certain things look more or less like prevalent.
Where? In the message itself?
Yeah, in the message itself, like between words that you actually want them to see.
Yeah, it's tricky.
So where we'd have
It's a little bit, yeah. So you could add in a bunch of X's, Y's, and Z's kind of randomly in the message. But a question would be, is that actually now then part of your algorithm for how you're encrypting things? So then you assume they would know what you're doing and would be able to easily undo it in some sense. Yeah.
Instead of just using one character to represent E, maybe use 4 or 5 different characters to represent the ones with the highest frequencies.
Interesting. Yeah, so maybe, yeah, over here.
Have a variable shift, so maybe first letter's 3, next letter's 4, next letter's 5, keep going.
Yeah, so maybe based on position in the alphabet, you can shift it by different amounts or different letters in the ciphertext. So that can maybe address some of the problems that we were talking about, right? Which is, one problem is this graph, right? So this is why I like thinking about it in terms of this, because you're just shifting this graph, right? You're not doing anything to change these letter frequencies. The other problems is the one-to-one mapping. So you have the letter L always maps the same letter, which again then manifests itself in this way, right? So we need some way to maybe get rid of that. So the one idea that we'll go with, and it's actually been done in kind of one of the classical crypto systems, is to make the key longer. So essentially it's combining multiple ideas that we've been talking about. So one is kind of the position aspect, so there'll be a different key based on position. And the key idea is, well, essentially, and the scheme is pretty kind of simple, but it's going to be more tricky to decrypt. But the idea is you still use the basic principles of a Caesar cipher. You're just going to have multiple keys that will encrypt multiple parts of the message. Yeah?
Can we write from right to left, instead of left to right, or would that be a different method?
I think you could do it. I would say that's part of your scheme of how you're sending the message. So yeah, if you're scrambling the message before it's being sent, it's essentially part of your crypto system. So it has to be analyzed the same, and you'd assume that they know that that's how you're doing it. But yeah, that would be interesting. And the idea is we're going to try to smooth out those frequencies so that the frequencies get closer and closer to where every character is uniform and equally likely in our ciphertext. So that the adversary has no way of knowing which one is actually the one we care about. Okay, so this is the Vigenère Cipher. I hope I pronounced that right. I'm sorry for people who speak French. The idea is similar to a Caesar cipher, but we're going to have keys as essentially a phrase. So, for instance, and we'll still keep our same scheme of messages and ciphertext. So it's going to be just A through Z. And we'll see that we can actually get awesome security properties from what we want. So let's say the message is the boy has the ball. This time our key would be a 3-letter key. VIG in this case. It could be whatever we want. And the idea being we're going to use the position idea and keep essentially repeating VIG. And the VIG, just like we saw that our key could be, we could represent our key as a letter or a number, right? So our shift of, 3, we could represent as D. No, our shift of 3 we'd represent as C. A shift of 4 we'd represent as D. So that would tell you how many characters to shift it by. And so the idea is, I want to show this. But I do want to keep this up here as a cheat sheet, so we don't have to keep going over this. Okay. Okay, so what I'm going to do is essentially write, so the key is just going to repeat over and over again over each of the characters. So it'll be VIG, G, VIG, VIG, surprisingly difficult. Okay, what do I do with this last letter? And do I write any I's? No. So essentially each character is going to be encrypted, meaning shifted by the amount that the key says on the letter above it. So T will be shifted by V, which is O, I will tell you. I'm gonna cheat a lot here. But like before, so if we're thinking about this in terms of a Caesar cipher, the key was V. You can think of it as exactly the same way, with just V all the way across. Because every